0.09. In his bundle, 0.03. So from the SA up to the bifurcation, it takes 0.16, 0.16, 0.03, 0.09, 0.12, 0.04 takes 0.16. From here to the endocardial surface of both ventricles, it takes just 0.03 due to the presence of Purkinje fibers. So, in the left side, the left ventricle wall thickness is more than the right. 0.03 at the left, 0.02 at the right. So, totally or in all, it takes 0.22 or 0.23. Second, till an impulse starts from SA to the entire surfaces of both epicardial surfaces. 0.23. Question? The fastest Purkinje fibers, the slowest AV node cells. Why? Because there is less gap junctions and a smaller nerve fibers. Conduction velocity in nerve is dependent on two factors: the diameter and the number of gap junctions. So in Purkinje fibers, the fibers has large diameter and more gap junctions. Question?
More gap junctions.
In the AV node, the conduction velocity is very low. Why? Because there is less gap junctions and less diameter. Question? So, now we want to record electrical potential that is coming to the surface of the body, which is called electrocardiography. We have already discussed the first part in the ventricle that is depolarized is part of the septum from the left to right. I have already discussed. If you have any question, we can review it again. From SA, an impulse initiates, passing from internodal pathway, AV node, His bundle, bifurcation, left and right. So, the atria depolarizes from the above to down. Since the atria is just like a circle and a sphere, so we will have a round wave. This is called P wave, which stands for atrial depolarization. So the atria depolarize from SA to the fibrous tissue, I mean the atrioventricular valve. So that is why we have a round P wave. Then, atrial repolarization cannot be seen in normal electrocardiography. The first part that is depolarized in the SA, in the atria, is the first part that is repolarized. So, you have P and then an atrial T, which cannot be seen in normal electrocardiography. So, the first part in the ventricle that is depolarized is part of the interventricular septum beneath the atrioventricular valve, from left to right. I showed you that this is resting state. This is two electrodes, the polarity minus a string galvanometer. When depolarization approaches to the positive pole of the string galvanometer, you will have a positive deflection. So, atrial depolarization make a positive deflection. Atrial repolarization make a negative deflection, P, and atrial T. We cannot see T in normal electrocardiography. Now the atrioventricular septum depolarizes from left to right. See? From left to right. Means depolarization is actually becoming from far away from the positive pole. That is why we have a small negative deflection in some ECG leads. I will discuss. This is called S wave. What is the reason for, Q wave? Q wave. What is the reason for Q wave? Depolarization of the septum under or beneath the atrioventricular valve from left to right. This is the reason for the Q wave. We can see Q wave in some EKG leads. Then the ventricle would be depolarized from the base to the apex, and then both endocardial surfaces would be depolarized. The lateral wall will neutralize each other. So the ventricle would be depolarized from the base to the apex. The last part of the both ventricles that are depolarized is somewhere in the base of the left ventricle. This is the base of the ventricle. And right ventricle. Somewhere, this is the aorta, and this is the pulmonary artery. This part is called pulmonary cone. In Farsi, مخروط ریوی. Cone means مخروط. See, this is just like a cone. These are the last part of both ventricles that will be depolarized. Again, see, depolarization is falling away from the positive pole. That is why you have a small negative wave here, which is called. Then, which one? Q wave. The first part in the ventricle that is depolarized is the interventricular septum beneath atrioventricular valve, which is depolarized from the left to the right. So, from the left to the right means depolarization is falling away from the positive pole of the electrocardiogram apparatus. That is why we have a small negative deflection here. Then the lateral wall neutralizes each other. So the left ventricle continue to be depolarized from the base to the apex. So halfway, then back to the resting state till here. Both endocardial and epicardial surfaces now are depolarized. The last part that are depolarized is part of the base of the ventricle at the pulmonary cone and posterolateral base of the right ventricle. So here the depolarization again from the left to right means is becoming far away from the positive pole. Then you will have an S wave. Now here, all the both surfaces of ventricles are depolarized. This is, I will describe T wave. Here, ST signifies that both ventricles are in depolarized state. Now, in the atria, the first part that is depolarized is the first part that is repolarized. This is not the situation we can see in the ventricle. Why? Because you have a high pressure in the left ventricle. this high pressure causes less nutrient to the endocardial surface of the left ventricle, the high pressure. How much is the peak pressure? 120. When the left ventricle is squeezed, less blood is coming to the endocardial surface of the left ventricle and also in the right ventricle. That is why the first part that is depolarized in the left or right ventricle would not be the first part that would be repolarized. Why? Lack of oxygen, lack of nutrients due to the high pressure, especially in the endocardial surface. It means that the repolarization lasts longer. Means that in the atria we have a longer refractory period. So since we have a longer refractory period, repolarization would be started a little later. So the first part that is repolarized in the ventricle is the apical surface, not the endocardial part, the epicardial part. See? This is the epicardial part of the left ventricle in the apex. Now they are all depolarized. When repolarization starts, see, we will have this situation. The vector, see, this is a vector. A straight line with direction. The vector of repolarization here in both ventricles is directed to the positive end. So when depolarization directed to the positive end, again you will have a positive deflection. That is why ventricular repolarization unexpectedly has a positive deflection instead of a negative deflection. See, in the atria, this is depolarization, this is repolarization. We would expect the repolarization in atria as a negative deflection. If ventricle repolarizes again from base to apex, but repolarization starts from apex to base, and the end of the vector directed to the positive, to the positive charges. So we will have a positive repolarization T wave, which signifies ventricular repolarization. Is that understood?
Yes.
Sure?
Yes.
Okay then. That will be part of your final exam. Q wave, S wave, T wave.
Can you explain the one between the Q and S? Please?
Q and S.
Yeah.
You see, resting. Then depolarization. We will have halfway, see, then back to the resting state. Did you get it?
Halfway then back to resting state.
You see, you have two electrodes here.
Yes.
When there is no potential difference between these 2 points, you have a straight line. When depolarization state, till halfway it will reach to the peak, then back to the resting, and then
Okay.
did you get it?
Yes.
Now we want to record these traces. We need two electrodes. Suppose that you are Dr. Reiter, Dr. Einthoven, sorry. In 1924, this electrocardiography brought him a Nobel Prize. Because before him, somebody by the name of Dr. William and quite a few other names have been brought electrocardiography, recorded electrocardiography from the heart of frogs and other animals. But Dr. Einthoven was the first one who introduced a stream galvanometer for the first time and then can record an interpretable electrocardiographic deflection and named them PQRST. He knows mathematics very well. And can work with vectors also very well. Now suppose that we are Dr. Einthoven and want to record electrocardiography. By the knowledge we have now nowadays. Now we know that we need at least 2 electrodes in order to record. But at that time the electrodes were very big. So it is wholly logical that if I want to record electrocardiography, I should put 2 electrodes nearest to the heart on the body surface. Am I right? So since the electrodes were very big, if I put 2 electrodes here near the chest, the electrical potential between 2 electrodes were very small that cannot be recorded. So first Dr. Einthoven put the electrodes near to the heart but on the torso, on the arm, left upper arm, right upper arm, left upper arm. These are 2 electrodes. So combination of electrode connection is called lead. This is 1 lead. Lead 1 between right arm and left arm. The second between right arm and left leg. The third between left arm and left leg. These are the electrodes. Now I should define the polarity. Right arm is always negative in a standard electrocardiography. Left leg is always positive. So between right arm and left arm, right arm is always negative, left arm is
Positive.
see? This is limb lead 1. Right arm is always negative, left leg is always positive. Limb lead 2. Left arm is always negative, left leg is always positive. Limb lead 3. Then Dr. Einthoven connect the vectors of these leads and make an equilateral triangle. This is called Einthoven triangle. See, limb lead 1, limb lead 2, limb lead 3. 1, 2, 3. Am I right? These are 3. Since we use 2 electrodes, it's called bipolar. Bipolar limb leads. Bipolar limb leads. Now, let us see what did he do. In electrocardiography, right leg is the neuter electrode. Neuter, N-E-U-T-R-E, neuter. Doesn't have any. Connected to the ground. See, when you wear rubber shoes and walk, there is a static electricity. And if you touch your classmate, there is an electricity. These electricity makes some noises, so you should emit them. Connect the right leg to the earth in order to emit unwanted noises. See? Because electrocardiography were very sensitive for the noises. Even these fluorescent make some noises. So connect the cable to the ground.
Sir, when you say ground, you mean connected to the floor?
Yes, to the floor. In order to discharge these static currents. Now, Dr. Guyton supposed that if I want to put the electrodes nearest to the heart, there should be another option for that. Listen, if I connect the wires from the right arm, and left leg to a high resistance source and make them zero, that would be the negative pole, and I have another cable that is connected to the positive pole. Make them zero. Then I put the positive pole nearest to the heart.
No, it's physics.
No?
It's physics now.
It is electricity, yeah. You see, connect the electrodes of the right arm, and left leg to a high resistance and make them zero. This is the negative pole, and now you have just one positive electrode. Put it near the heart. Fourth intercostal space at the right sternal border. This is V1 or C1. Fourth intercostal space at the left sternal border. This is C2 or V2. Set aside C3. Put C4 at mid-clavicular line at the intersection of fifth intercostal space. This is V4. Now put V3 between V4 and V2. Make three lines out of your armpit: anterior, middle, and posterior axillary line. Put V5 at the fifth intercostal space at the left on anterior axillary line. And then V6 mid axillary line. You have 6 chest electrodes. These electrodes, these leads actually are unipolar. These are unipolar, just positive. Now, you can connect this unipolar electrode to the right arm, to the left arm, and to the left leg. These are unipolar limb leads. You have three unipolar limb leads, 3 bipolar limb leads, and 6 chest leads. In all, you have 12 reference leads, 12 hexagonal reference leads. 1, 2, 3, AVR, AVL, AVF. Since they are very weak, Dr. Einthoven augmented them and called them augmented vector for right hand, AVR, augmented vector for left hand, AVL, and augmented vector for left foot, AVF. AVR, AVL, AVF, these are unipolar limb leads. 1, 2, 3, 1, 2, 3, limb lead 1, limb lead 2, limb lead 3. These are 3 bipolar limb leads and 6 chest leads. In all, we have hexagonal, hexagonal left reference system. In clinic, you can connect these left chest leads to the right. This is not the standard hexagonal reference system. Connect these left side leads to the right and make the electrical difference of the right ventricle. Otherwise, the right ventricle the electrical changes, is actually seen in a mirror shape on the left. In order to have the true shape, you can connect these left chest is to the right and make a clear picture that is happening in the right ventricle. This is actually done in clinic. Now we have 12 hexagonal reference system. Any question up to here? No. Now listen.